This is the second of two lessons on rings. In this lesson, I'm going to talk about ideals and quotient rings. An ideal I is a subset of a ring R with special properties, which I'll mention in a second. Ideals generalize certain subsets of the integers, such as the even numbers or the multiples of positive integer n. The two defining properties of an ideal is one, it's a subgroup of the ring. So an ideal is closed under addition and has additive inverses as well as the additive identity. And then there's the ideal property, sometimes called the absorbing property. An ideal is closed under multiplication by any element of the ring. An ideal can be used to construct a quotient ring in a way similar to how, in group theory, a normal subgroup can be used to construct a quotient group. I'll talk about quotient rings later in the lesson. So more formally, just putting these two conditions down a little bit more precisely, a subset I of a ring R is called the left ideal of R if it satisfies the following two conditions. So I is an additive subgroup of R, and then for every element in the ideal and every element in R, if you multiply R times X, you'll get another element in I. So that's where you get this absorbing idea from. Another way of writing that is R for any element in the ring times I is a subset of I. So in a sense, it absorbs anything that you multiply on the left. A right ideal of R is defined in a similar manner. So we just have the R multiplied here on the right. If the subset of R is both a left and right ideal of a ring R, then we just say that I is a two-sided ideal, or a lot of times you'll just see the term an ideal with the assumption that that means two-sided, and if you need to be more specific, you would just say right or left ideal. In a commutative ring, all ideals are two-sided. And then just one last point here. Keep in mind that an ideal is not required to have a multiplicative identity, and thus it is not necessarily a subring of your ring R. For a given ring R, the ring itself is an ideal. This is known as the unit ideal. The subset of R consisting only of the zero element is an ideal. This follows from theorem 20I, where I've proven this in a previous lesson, but I've copied the result up here for you. It's just saying 0 times any element from your ring R is 0 again, so you just generate the set with 0 in it. That's known as the zero ideal. Not very interesting, nor is the unit ideal. An ideal of a ring that is neither the unit nor the zero ideal is referred to as a proper ideal of R. We have a theorem related to that. If a left ideal contains a unit, in other words, a multiplicative inverse, then it cannot be a proper ideal. And we can do a similar result for right ideals, but I won't prove that here. The proof looks almost the same as what I'm going to show you. So let I be a left ideal in a ring R. Assume that U, element of I, is a unit, and that its inverse, its multiplicative inverse exists. And then take any R, an element of our ring. Since R as a ring is closed under multiplication, we have R times U inverse is an element of R. And then from the definition of our ideal, we have this element from R times an element from the ideal has to be in the ideal by definition. And this turns out to equal R, right? The inverse times U just gives you the multiplicative identity. And thus every element of R is in our ideal. In other words, the ideal equals all of R, and it's not a proper ideal. It's actually the unit ideal in that case. there's something known as a principal ideal, and we can define those for either commutative or non-commutative rings. It's basically an ideal generated by one element from your ring. In the commutative case, the principal ideal generated by A is defined as all multiples of A by every element of R, and we write it out like this, and this is the notation. And of course, if you have a commutative ring, it doesn't matter whether you're multiplying on the right or the left. However, if you have a non-commutative ring, it gets a little bit more complicated to define a principal ideal. There's three cases. If we want a left ideal, then we define it as this set here, basically all the multiples from the ring on the left of A. And if we want a right ideal, then it's all of the multiples of A multiplied by different elements from R on the right. And then in the two-sided case, if we want a two-sided ideal, it's all the sums of this form here, where you have R and S elements from R, and A is in the middle here. I'll explain why you get this more complicated definition in the case of a two-sided ideal when you have a non-commutative ring. On the next slide, I'll give you the reasoning behind that. It looks, on the surface, it looks like it's a bit overly complicated, but there's a good reason for this. So in the commutative case, then all three of these definitions are equivalent, and you just fall back into this definition here. And in all cases, we do use this notation. Sometimes you'll see like a little subscript R under this one, and for right, and then it's little subscript L for left under this one here. And then for the two-sided one, you can make some other notation. But usually it's clear from the context which one of the three you want to talk about in the case of a non-commutative ring. On this slide, I'm going to explain the definition for a two-sided principal ideal in the case that we have a non-commutative ring. But first, let me explain why we don't need any type of summation in the one-sided case. For example, consider left ideals. If we take two elements in our left ideal, A, then when we add them together, we can use the distributive law to get this form here. But then this R1 plus R2 is in R, and so this is again in our ideal A, and so we have closure. We can do the same thing for the right ideals, right principal ideals, I should say, and we would have closure again. The problem with the two-sided ideals is with closure, in fact. If we naively try to mimic the one-side definitions, we might try this here, without the summation over the R and S in R. So let's see where we run into a problem here. We'll first check to see if it's a left ideal. So we'll take T and R and X and S, our proposed ideal, and we want to show that Tx is in S. In fact, it is. So we first know that X, being in our proposed ideal, can be written in this form here. Then T times X has this form here, just plugging in X, and then we can group the T and the R together. But T times R is actually an R. So we get something in the form R prime, A prime, S prime, where R equals RTR and S prime is just S. And so we have closure under left multiplication. So it is a left ideal. This thing here is a left ideal. It's also a right ideal. We're just using the same values for T and X, and now we multiply on the right, and we get RAS, plugging in RAS for X times T. Then we group the S and T together, and then we have this form again where R prime equals R and S prime equals ST. So this is in the form of something in the ideal. So we have closure under right multiplication. Excuse me. The problem is closure under addition when we look at it in terms of being a two-sided ideal. And if we take this and this from our proposed ideal, there's no way that their sum, that we can write this sum in the form RAS. We can't factor out the R or the S. They're different values. And so unless we have a very special type of ring, for example, a ring with a multiplicative identity, and we take A is 1, where we get S equals R in that case, other than something like that, we're not going to get an ideal using this definition here. So we're just going to get single terms RAS, and we're not going to be able to get any closure under addition. So in order to get closure under addition, we need to take all possible sums as we defined it in the previous slide. So a bit long-winded, but just to give you some background as to why we need a more complicated definition for a principal two-sided ideal in the case of a when the ring doesn't have commutativity. I have a couple of examples on this slide. The first one is the even integers. That's a principal ideal in the ring of all integers. The generator is 2. We can check to see that it's a principal ideal. First, it has to be an additive subgroup, which it is. If you add two even numbers, you get another even number. You have inverses, additive inverses, I should say, and you have the 0 element in 2z. Then we want to show the absorbing property, which I've talked about down here. For every x in 2z and r and z, we have an even number times an integer, r, which could either be even or odd, but in either case, that when you multiply an even times another integer, you get an even number. So Rx is an element of our ideal 2z. Thus, I is a left ideal. And we can just, if you flip the order here, the same reasoning gives us that 2z is a right ideal. So we have that, and we're talking about a commutative ring here. So in the integers, so that means we have a two-sided principal ideal. And we have the same idea if we have n times the integers, just writing it out here longhand. So we can take any integer other than 2, 3, 4, whatever, and multiply it times all the integers. And again, we'll get a principal ideal. And using the same reasoning that I used up here, we can show that it's both this thing here, nz is a additive subgroup of the integers, and it has closure when you multiply either on the right or the left, which I wrote out some of the details here. So I'll give you a second just to look at that. Okay, then going on to the second example, the set of all polynomials with real coefficients divisible by x squared plus 1, and exactly divisible, in other words, with no remainder, is an ideal, call it I, in the ring of all real coefficient polynomials, Rx. We can show that here. First, we need to show it's a subgroup. So if we take two functions, f and x, in our proposed ideal, then the sum, of course, if each one is divisible by x squared plus 1, then the sum would be. So we have closure. The 0 polynomial is divisible by x squared plus 1. So we have the 0 element in our ideal. And then if f of x is an element of our ideal, minus f of x is also, because that would still be divisible by x squared plus 1. Associativity and commutativity in I are inherited from the R, in other words, this thing here, the set of polynomials with real coefficients. So I our proposed ideal is an abelian subgroup in R of X, our ring, and then we just need to show the absorbing property. We can do it on the right or the left. I did it on the right here, but it's just it's easy to do it on the left. So if x squared plus 1 divides f of x, then it's going to divide the product of f of x times any other polynomial in our ring. And we can do the same thing multiplying on the left. Okay, so there's 2 examples. Let's continue a little bit more on this topic. I have 3 more examples of ideals on this slide. These are not principal ideals, but just ideals. And I'll leave the details to you to verify that each one is a subgroup of the ring, as well as having the absorbing property. So the first example, in the ring of continuous functions from R to R, from the real numbers to the real numbers, under pointwise multiplication, the subset of functions f, such that f of 1 equals 0, is an ideal. Another ideal in the ring of continuous functions is a set of functions that vanish for sufficiently large values of x. In other words, continuous functions for which there exists a value L such that f of x equals 0 when the absolute value of x is greater than L. In other words, when x is greater than L or x is less than minus L. Then the third example is of ideals that are left ideals but not right ideals, and right ideals that are not left ideals. So we'll take the ring of all n by n matrices over any ring. This is the notation for that. And then first we'll look at the subset of matrices that have the row I consisting of zeros. This is a right ideal, and just a note here, so I'll give you part of the proof that this is a right ideal. If you take A from this set, that, in other words, matrix A that has zeros in row I, and you multiply it times any other matrix from our ring, then the product AM has all zeros in row I. Thus, we have this absorbing property. You still need to show it's a subgroup. I'll leave that to you to verify. So I sub row of I, in other words, the set of matrices that have zeros in row I, is a right ideal, but it's not a left ideal. I'll leave you to check that. On the other hand, if you take the set of matrices from this ring that have zeros in the jth column, then that's a left ideal, but not a right ideal. For even more examples, check out the Wikipedia article entitled "Ideal and Ring Theory" in quotes, in brackets, excuse me. I'll give you a link to that in the information to this video, and also give you a link to pointwise multiplication. It's just multiplying two polynomials together. It's what you might think, but I'll give you a link to the precise definition of that. That's also a Wikipedia article. On this, in the next few slides, I'm going to talk about the second topic of this lesson, something known as a quotient ring, also known as a factor ring. It's a structure like a quotient group. Given a ring R and a two-sided ideal I in R, we can construct a quotient ring denoted R/I, whose elements are the cosets of I in R, where the cosets of I in R are defined in a similar manner to the cosets of a subgroup within a group. So given any R in R, our ring, R, small r plus I, is the set of all elements of this form here, R plus ranging x over the values in our ideal, two-sided ideal, and that's is a coset of I in R. The set of all cosets of I in R comprise the quotient ring of I with respect to the ring R. A quotient ring is a ring that is constructed from another ring called the parent ring. So in our explanation up here, R would be the parent ring and I is the quotient ring. By dividing out, so to speak, that's why I'm using the slash here, dividing it out by an ideal. Formally, the elements of R slash I are the equivalence classes of R under the equivalence relation tilde, defined by, and I'm not sure that's the right name for this, but I'll call it that, it's this squiggly line, defined by x tilde y, if and only if x plus the inverse of y, additive inverse of y, is an element of the ideal. The addition and multiplication operations on R slash I, are defined as follows. It's pretty straightforward. So if you add two elements from the coset, it's just x plus y plus I. And then if you multiply, you just multiply the two representative elements here. It can be shown that these operations are well defined and that R slash I is a ring under these operations. The key to understanding a particular quotient ring is to identify the cosets, otherwise i.e. the equivalence classes. So let's look a little further into this description here. I have a couple of examples on this slide. Given a ring R, the quotient ring R slash the set with 0 in it is equivalent to R. Since each coset, R plus 0, the set 0, equals R plus X, where X is an element of the set with 0 in it. In other words, X equals 0 all the time. And that means that for each R, we have a different coset, and that implies that the R slash 0 is equivalent to R in terms of the number of cosets. On the other hand, the quotient ring R slash R has but one coset. And the reason for that is if you write this out, this is what you get here, but you can take X to be minus R plus whatever value, whatever element of R you want, and so you can generate all of R, just saying it's equivalent to all of R. It generates all the elements in R, regardless of what value of R we select. So there's just one coset, which is equivalent to the 0 element and of R slash R. In general, the larger the ideal, the smaller the quotient ring, R slash I. If I is a proper ideal of R, i.e. I doesn't equal R, then R slash I is not the 0 ring. Then we have a second example here. Consider the ring of integers z and the ideal of even numbers. The quotient ring z slash 2z has only two elements. The coset 0 plus 2z, which gives us back all the even numbers. That's kind of following this first example here for something more specific. And then the other coset is 1 plus 2z, and that gives us all the odd numbers. So z slash 2z is isomorphic to the integers mod 2. In fact, you'll see in some textbooks they'll use the notation z slash 2z rather than z mod 2. On the next few slides, I want to talk about an example concerning a polynomial ring, Rx, where R is the real numbers, and we're talking about polynomials that have coefficients from the real numbers. And the quotient ring, Rx slash I, where I is the principal ideal generated by the polynomial x squared plus 1. So in other words, I equals all polynomials of this form here, ax, where ax is from the real polynomials, times x squared plus 1. So it's basically everything that has a multiple of x squared plus 1. That's the ideal that we've defined here. A coset of Rx slash I is of the form g of x plus I, and that equals the set g of x plus a of x times x squared plus 1. So basically terms from the ideal plus any polynomial from these, I guess from this set here, r of x. The zero element of r slash I is x squared plus 1 plus I. So the coset x squared plus 1I consists of all multiples of x squared plus 1. Further, we have that x squared plus 1 equals 0 with respect to the quotient ring, which implies x squared equals minus 1, or x equals the square root of minus 1 equals the imaginary number I. So a little bit of abuse of notation here, but you'll see why I've done this later. Using the division algorithm for polynomials, and I'll give you a link to this. You may have seen it in high school algebra where you take one polynomial and divide it into another. It looks very similar to long division for just numbers. So if we use this here and we take any g of x from our ring r of x, we can write it in this form here. Basically, you take the multiples of x squared plus 1 and multiply that times some q of x, and then there's some remainder. And it may very well be that q of x is 0, and you just have a remainder here, where the remainder is linear. So that's part of this algorithm. The remainder is of degree less than this polynomial x squared plus 1. So it would be of the form ax plus b for constants a and b from the real numbers. And q of x is a real polynomial. So an arbitrary element of Rx slash I, this quotient ring, is of the form ax plus b. The operations of the quotient ring are exactly the same as those for complex numbers. More formally, Rx slash x squared plus 1, in other words, this quotient ring, is isomorphic to the complex numbers under this mapping here. And to prove this, we need to show the two properties for an isomorphism, which I'll do on the next slide. So we'll take two elements from this quotient ring, these two here, and then we'll show that the two properties for an isomorphism follow through and are true. So let's go to the next slide to see that. So let's check the two properties for an isomorphism. First, we have f of the two terms multiplied together. Then we get AC x squared plus AD and BC times x, and then BD. But we know that x squared equals minus 1. So this reduces to this here. You notice we get a minus AC here. And then we just use our definition of the function, so the ADBC times I, and then plus BD minus AC. And then we take the function of each one of these terms separately and multiply them. And we want to get the same thing as we have here. So we have f of ax plus b, and that's ai plus b, and then f of cx plus d, and that's ci plus d. And when we multiply them together, we get BC and AD times the imaginary I. So that's good, that matches up. And then for the real part, we have BD, and then we have AI times CI, but then the I squared is minus 1. So we get BD minus AC. So these two match up. And so we have that part of the isomorphism property. Then we need to do the same thing for addition. So we want to show this, f of the sum here equals f of this plus f of this. We can just expand them out. We just collect the terms times the x, and then the constant terms, and then we use our definition of the function. We get this here. Then here we just apply the function individually to each term, and then we collect the things that are multiplied times the imaginary I, and then we collect the constant terms, and of course these two are the same. So we've shown that Rx slash x squared plus 1 and the complex numbers are isomorphic as rings. We can generalize our previous example. Let R be any commutative ring and Rx be the polynomial ring defined over R. In other words, have the polynomials that have coefficients from this general ring R. Take any nth degree polynomial in Rx, i.e. f of x equals something of this form here, and form the principal ideal generated by f of x. So in other words, all multiples of f of x by elements from our ring Rx. The coset of the quotient ring Rx slash I is of the form gx plus I. So it's all polynomials of this form here, g of x plus a of x times f of x, where the a of x ranges over the ring R of x. However, by the division algorithm, which we employed in the previous example, we can write g of x in this form here, where you have q of x times f of x plus some remainder. Now in this case, the remainder is less than degree of f of x, so it's of degree n minus 1 or less, so it's of this format here. So the cosets of the quotient ring Rx slash I are polynomials of the form g of x plus I, just taking what we've written here over, but then we can plug in this for g of x, which I've done, and then you can collect the this second term here, third term, excuse me, and the first term, and they both have a factor of f of x. So this part here gets absorbed into the ideal, and you just have the remainder. So this essentially is equal to Rx plus I. That's the coset that it's representing, and so the cosets are basically isomorphic to polynomials of degree n minus 1 or less over the this arbitrary ring R. Okay, so that was the last slide in this lesson, and this is the second of 2 lessons on rings. Now I'm going to go into fields in the following lesson.